Okay, good evening. engr315 heat transfer. Okay, so today we are going to continue talk about the chapter 5 convection heat transfer over a flat plate boundary layer. Today we're going to talk about the turbulent boundary layer. Okay, let me switch my screen. Okay, we have all the equations for laminar boundary layer, right? Now let's review the turbulent boundary layer. What does it look like? Remember, we mentioned it before, no matter how turbulent it is, but for a flat plate, at the beginning is always the laminar boundary layer, okay? Then if it's long enough, it becomes turbulent, okay? So you have a critical Reynolds number. Critical Reynolds number, most of cases, 500,000, 5 by 10 to the 5, okay? Local Reynolds number equal to 5 by 10, 5. This is a critical Reynolds number. Sometimes in some application, the critical Reynolds number might change, okay? Might differ from 5 by 10, 5. But most of the time, that's what we treat as a critical Reynolds number, okay? Before that particular location, X, is laminar boundary layer. Then after this location, it becomes turbulent boundary layer. Okay, so all the turbulent boundary layer, actually they include a laminar portion at the beginning. Okay, so again, similar to the laminar boundary layer, we have several equations. Okay, first of all is the boundary layer thickness. Okay, so boundary layer thickness is, you can use this equation. If the Reynolds number is greater than 5 by 10 to the 5, it will be 0.16x divided by Reynolds number x1/7. Okay, these are the empirical solutions. It's not theoretical. Okay, I can send you the file later. Okay, let me write it down first. So thickness. So you at every location, any location x. Okay, so you should be able to calculate the thickness on that particular location of the plate. Okay. Of course, for the flow side, you have lowercase cf 0.455 over log square 0.06 Reynolds number x. It's also local value, lowercase cf. Okay, local skin friction coefficient. So you can calculate on any location. You can calculate the shear stress. Okay, like this, local shear stress. Okay, again, when you use the capital CF, average overall CF. Okay, so you can use this CF to calculate the overall shear force. Okay, overall average shear stress and overall shear force over log square 0.06 Reynolds number L. Notice I use Reynolds number L. That's overall Reynolds number to the end of the plate. Okay, minus 1520 over Reynolds number L. Okay, so the flow side, you should be able to calculate everything. Okay, based on this. So you can have, we have the example before, right? You should be able to calculate the shear stress, overall shear stress, overall shear force, resistance force of the plate. Okay, this equation including this CF equation, it's for the entire plate. It is a shear stress, skin friction, overall average skin friction coefficient for the entire plate, including the laminar portion. Okay, I think that makes sense. That makes life easier for your calculation. You don't have to separate the portion, right? This is the overall, okay, including the surface. Okay. Now, heat transfers. So again, we're gonna use the Reynolds analogy, right? Okay, do you remember what's the equation, Reynolds analogy? Stanton number, right? Prandtl number to the 2/3 equals to skin friction coefficient capital CF/2. Okay, so this is the Reynolds analogy we show you last class for the laminar boundary layer, but here it still stands, right? So based on the relationship between CF and the Reynolds number, okay, so you can actually have another correlations to find out the Nusselt number, okay? So obviously the Stanton number, that H there, right? And the CF, you have a Reynolds number there. So, okay, so Nusselt number, that's equation 5.85, okay? Average Nusselt number equals, oh, by the way, here I'm emphasizing on the average values, okay? So the fluid mechanics of the turbulent flow is very, very complicated, and it's chaotic, and you don't have an analytical solution. But for engineering application, the overall characteristic is what we interested, even with the turbulent conjugate flow. So it's overall Reynolds, average Reynolds number will become average H over L over K, right? That's the equation between Nusselt number and the heat transfer coefficient. Then it become Prandtl number 1/3, okay, times 0.037 Reynolds number L to the power of 0.8 minus 871. Okay, so you can use this to calculate for the turbulent boundary layer, the Nusselt number and the heat transfer coefficient. Okay, so there's a couple ranges here. Okay, so this equation is for Reynolds number. So we have Reynolds number greater than 5/10⁵ is for the turbulence region. This one for relatively small Reynolds number, less than 10 to the 7th, if I remember correct. Yeah. So between 5/10 to the 5 to 10 to the 7. Okay, so in that Reynolds number range, so the plate is long, but it's not very, very long. Okay, longer than the critical Reynolds number, right? 5/10⁵, but it's not long, very, very long. Okay, it's not very long. So in that median range, the overall Nusselt number, overall heat transfer, average Nusselt number and average heat transfer coefficient can be used. You can use this equation to calculate. Okay. Again, this is the average, including the laminar portion. Okay, that's great, right? The average heat transfer coefficient, includes the laminar portion overall. Okay, average. So for greater than 10 to the 7 and less than 10 to the 9. Okay, you have another equation. Yeah, it's a little bit longer equation. Okay, equation 5.858. Okay, so average Nusselt number equals to H over H times L over K equals, let me see, it's pretty dark here. Okay, 0.228. Okay. Log Reynolds number L to the power of negative 2.84 minus 871 times Prandtl number 1/3. Okay, the experimental correlation. So this for the satisfy for the Reynolds number greater than, now let's do this, greater than 10 to the 7 and less than 10 to the 9. Okay. So this is, I think that's equations I want to introduce. Okay, so notice these are this equation for natural number and the heat transfer coefficient is based on the Reynolds analogy. Okay, so but I don't care about the derivation. Okay, as long as you know how to use these equations. Boundary layer thickness, physically boundary layer thickness. So this is the flow boundary layer thickness, right? Thermal boundary layer thickness, you can get the same equation from the laminar. Okay, so that ratio, right? Prandtl number. And this is local skin friction coefficient. And this is average skin friction coefficient. And the Reynolds analogy, based on that, we can calculate the Nusselt number or heat transfer coefficient, average heat transfer coefficient. Okay, so we'll do some calculation. So let's do an example. Okay. Okay, let's see example 5.9. Oh, by the way, forgot. This is for the isothermal. This is the isothermal, okay? Isothermal boundary. Okay, so iso heat flux. We don't have a bunch of equation for iso heat flux. It's based on isothermal. So the Nusselt number for iso heat flux equals to 1.04 times the Nusselt number for isothermal. Iso heat flux. Okay, so flow boundary layer is the same. Doesn't matter what kind of a temperature condition in the boundary, but the thermal boundary layer is changed a little bit. Okay, the Nusselt number. So heat transfer coefficient is 4% more. Okay, if you use iso heat flux condition. Okay, so this is just one equation you need to remember. Equation 5.87. So let's look at example 9. Okay, it's not difficult, right? 20 degrees Celsius, 1 atmospheric pressure flow over a flat plate. So a flat plate velocity over the flat plate is 35 meters per second, right? Okay, 75 centimeter long. Okay, and the maintained at a 60-degree temperature, TW equals to 60 degrees Celsius. So it's isothermal condition. It's easy. Assume unit depth in the Z. So in the Z direction going to the paper is 1, right? Unit depth. Calculates the heat transfer from the plate, total heat transfer. Total heat transfer equal to what? H times A times TW minus T infinite. Okay, what is the T infinite? 20 degrees Celsius, okay. Okay, so that's the equation we will try to use. So start from the question, right? The equation from the question is pretty straightforward. So so I guess the problem is to find out the H bar, right? Area is 0.75 meter times 1 meter, okay? And the temperature difference is 40 degrees Celsius, okay? So H bar, okay? What equation can we use? Okay, now you have 2 equations for Nusselt number, right? Okay, so which one to use? So which number you need to check to see which one to use? What's the difference between these 2 equations? Well, equation look different, but the condition is different, right? One is for the Reynolds number less than 10 to the 7, greater than 10 to the 5, right? For turbulent region, it has to be greater than 10 to the 5, or 5 by 10 to the 5. Okay, less than 10 to the 7. The other equation is greater than 10 to the 7, less than 10 to the 9. Okay, so in that sense, for this type of problem, definitely you need to check a Reynolds number. Okay, what the Reynolds number is? Velocity, okay, times the length. Total length is 75 centimeter divided by viscosity. Okay, velocity is 35 meters per second times 0.75. What is the viscosity? So you need the properties, right? So if you find a property, we need a temperature. What temperature do we use? Remember? Okay, film temperature. Okay, so half of the 60 watt temperature plus the ambient temperature. So it becomes 40 degrees. Based on the 40 degrees Celsius, I think we get the property viscosity equals 1.906 times 10 to the negative 5. Oh, this is dynamic viscosity. We need a kinematic viscosity, okay? So this is dynamic viscosity, mu. So our equation will be mu here, so it's rho, the density up here. Density I have to give you. So this is the kilogram per meter second. So density for this is based on the ideal gas law, is 1.128 kilogram per cubic meter. Okay, so substitute this density 1.128 and down there 1.906 times 10 to the negative 5, right? Yeah. Okay, I have to write to the next page. Okay, our Reynolds number based on that calculation is 1.553 by 10 to the 6, okay? Okay, now, is that greater than 10 to the 7 or less than 10 to the 7? I think it's less, the 10 to the 6, right? So we use this equation, right? This equation, okay? So based on this equation, I think, do we have everything? Well, we need a Prandtl number. We have the Reynolds number, right? So we need a Prandtl number. So the Prandtl number, okay, let's write this thing again. So based on this Reynolds number, Nusselt number, average Nusselt number, H L over K, right? I need a K too because I need to find the H equals, I cannot remember that equation. So I need to write it down, look at it. So it's Prandtl number times 0.037. Reynolds number to the power of 0.8 negative minus 871. Based on this, we need the property for K, right? Again, film temperature is 40 degrees based on the previous page, on the previous page. So K is what? K, I think from the appendix, you should be able to get K value for 40 degrees Celsius, 0.02723. Watt meter Celsius. Okay, what else you need? And the Prandtl number. Prandtl number is there too. For this case, Prandtl number is 0.7. They're air, right? It says, yeah, 20 degree air. Okay, so obviously 40 degree. Prandtl number 0.7 for the air. So I guess you need you have all the information. Reynolds number already have this, and you need the Prandtl number. Then you have the length, right? Length is 0.75. K is this. So our average heat transfer coefficient for this problem is 79.1 watt per meter squared C. Okay, so then we'll come back to the equation. We can calculate the total heat lost. Okay, based on this equation, H times 0.75 times 40 degree, HA delta T, right? So our total heat loss is how many watt? 2,373 watts. Okay, so this is the example to use the turbulent boundary layer equations to calculate the total heat transfer. Okay. Yeah. Okay, so I think that's about it for the surface boundary layer surface heat transfer for the boundary layer flow. Okay, next time we're going to talk about the flow inside the tube, in-tube flow. Okay, heat transfer of the in-tube flow, also convection. Here is a flat plate convection, right? So boundary layer. I think I gave you plenty of equation, more than enough equation for you to digest. And I will assign some homework for you to practice. Okay, so this is a good example. Okay, so